Welcome back to The Explainer. Today, we're cutting through the absolute noise surrounding three of the most overused and honestly most misused terms in tech right now: AI, machine learning, and deep learning. You literally hear them everywhere, often used interchangeably like they're the exact same thing. But under the hood, they represent entirely different approaches. So let's clear up the buzzword soup.
It's a completely fair question. You hear these tossed around in marketing pitches, and you have to wonder, are they just different flavors of the same thing? Spoiler alert, no, they absolutely aren't. They're actually nested layers of technology, kind of like Russian nesting dolls, with each one building upon and getting more specialized than the last. Today, we are going to zoom right in on exactly how they work, stepping layer by layer into the core of modern computing.
Okay, here is our roadmap for today. 1. The artificial intelligence umbrella. 2. Machine learning and its data-driven approach. 3. Deep learning and neural networks. 4. Generative AI and LLMs. And finally, 5. Choosing the exact right approach for your needs.
All right, let's kick things off with Section 1, the artificial intelligence umbrella.
So let's start at the very top. The crucial thing to remember is that AI is really just a giant umbrella term. We're talking about the entire overarching field focused on designing systems that can emulate human reasoning, learning, and problem-solving to automate complex tasks. Whether we're talking about a basic non-player character in a video game following a preset path, or a cutting-edge medical diagnostic tool, if a machine is mimicking human intelligence, it fits right here under this massive umbrella. It's the whole shebang.
Now, under that big umbrella, things split up into a few very different approaches. For example, contrast what we call symbolic AI with data-driven AI. Symbolic AI is kind of the old-school method. It runs on explicit business rules and decision trees, basically a super strict instruction manual written by a human. Like, the rule might literally just say, if a user is between 25 and 40 years old, recommend product X. Boom, simple. But on the flip side, we have data-driven AI. This approach optimizes its decisions by analyzing mountains of data to find underlying correlations that are just way beyond human judgment.
Which leads us perfectly into Section 2, machine learning, the data-driven engine.
So we take a step deeper inside the AI umbrella and we find machine learning. ML completely shifts the paradigm. Instead of programming those rigid, strict rules we just talked about with symbolic AI, we basically just feed the machine a ton of historical data and say, here, you figure out the patterns. It's highly predictive. Essentially, if the machine can figure out the hidden logic behind the old data, it can accurately guess what brand new, unseen data is going to look like. The workflow usually looks something like this. First, you feed in your past training data. The machine learning algorithm chews on it, learns the ropes, and builds a logical mathematical model. Then, it uses that newly established model to predict outputs whenever fresh data comes in. This is exactly how your email provider catches spam, right? It learned from millions of past emails what spam looks like, and now it predicts the outcome for every single new message that hits your inbox. Now, depending on what you're actually trying to pull off, machine learning splits into three main paths based on how you train the algorithm. First up, supervised learning. This uses labeled data where the answer is already known, like predicting tomorrow's sales based on historical weather forecasts. Then you've got unsupervised learning. This is where the machine searches for hidden patterns in totally unlabeled data, like grouping similar types of customers together out of nowhere. And finally, reinforcement learning, which is honestly fascinating. It operates on a feedback loop of rewards and penalties, kind of like training a puppy. You literally reward the system when it makes the right move.
Okay, so machine learning is a powerhouse, no doubt. But what happens when your data is simply way too complex for those standard algorithms to handle? It's a huge question, because standard ML just kind of hits a brick wall when dealing with massive, highly unstructured data. Think about processing the chaotic nuances of human speech, or trying to recognize one specific face in a massive crowd. Standard math models just can't keep up.
And that brings us to Section 3, deep learning and neural networks.
To solve that messy data problem, we zoom in even further to the deepest layer of our nesting dolls, deep learning. Deep learning completely drops those traditional mathematical models. Instead, it uses complex, multi-layered neural networks that are heavily inspired by the biological neurons in our own brains. This crazy architecture allows the system to capture incredibly intricate patterns and pull off high-precision tasks, like autonomous driving or real-time computer vision.
Think of these artificial brains like a sandwich. You've got an input layer to catch all the raw data, multiple hidden layers in the middle doing the heavy lifting and transformations, and finally an output layer that delivers the ultimate guess. Now inside those hidden layers are tunable elements we call weights and biases.
Think of weights like little dials that control how strongly a specific feature influences a decision. For example, the word prize might heavily weight an email toward being marked as spam. And biases? They're sort of like built-in nudges that help a neuron fire even if the raw input is a little weak.
Training these networks basically boils down to 4 crucial steps that repeat over and over again. Step 1, the forward pass. The network looks at the data and makes a guess. Step 2, error calculation. It uses a loss function to see exactly how badly it messed up that guess. Step 3 is backpropagation. Great word, by the way. The system literally runs backward through the entire network to see which of those weights and biases caused the error. And step 4, the weight update. It subtly adjusts all those little dials so the next guess will be just a bit sharper. It repeats this cycle millions of times until it gets ridiculously smart.
All right, shifting gears a bit, let's hit section 4, generative AI and LLMs.
Let's talk about the elephant in the room. Because tools like ChatGPT have gone totally viral. The general public pretty much assumes that all AI just means generative AI. We hear the word AI in the news and immediately picture a chatbot. But as we've just mapped out, generative AI is really just one highly specialized little branch sitting on top of deep learning. It's just that it finally made these massively complex models accessible to everyday consumers, which is exactly why the public discourse gets them so mixed up.
To be super precise about these viral tools, we need to compare generative AI with LLMs, or large language models. Generative AI is the broader category here. It covers creating new content across all types of media, generating brand new text, stunning images, or even totally synthetic audio. LLMs, on the other hand, specialize specifically in language-related tasks. So, an LLM like GPT is a type of generative AI for sure. But a tool that generates a picture of a cat on a skateboard, that's generative AI, but it is not an LLM.
Bringing it all together now in section 5, choosing the right approach.
So you've got all these nested layers now, right? How do you actually know which one to use? Well, the choice almost always comes down to your resources and the complexity of your task. If your project has moderate amounts of data and standard computing power, like predicting customer churn or flagging basic fraud, sticking to standard machine learning is totally the way to go. But if you have absolute mountains of unstructured data, like thousands of hours of raw video, and you need pinpoint accuracy for something like multi-object recognition, you have to go with deep learning, which demands massive data volumes and serious, heavy-duty computing power.
It's all a balancing act. Standard machine learning is incredibly efficient at automating tasks and handling everyday data applications. But balancing on the other side, you always have to weigh the heavy costs of acquiring all that data in the first place, the pressure of picking the exact right algorithm, and the very real possibility of high error rates if your model isn't trained on clean, solid data.
And that leaves us with a truly fascinating thought to wrap up on. As raw computing power, especially stuff like quantum computing, accelerates in the coming years, these nested models are only going to get deeper, faster, and wildly more complex. Will the boundaries between our own human reasoning and these advanced artificial neural networks eventually just disappear entirely? It's definitely something to chew on, because our very definition of intelligence is about to be tested like literally never before. Thank you so much for joining me on this explainer. And remember, keep questioning the buzzwords.